Well, hello again. This is Matt Roscoe, and a lecture for our course M573, Teaching Geometry for Teachers. This week we'll take a look at transformational geometry. So I want to, basically discuss, well, what is this thing, transformational geometry, and then take a look at a paper-based exploration of reflection. So dive right in with some sort of hands-on thing, and then I guess do formally define what transformation is, formally define what symmetry is, and then take a look at the three isometric transformations in grades 512. It's actually K12. And then do another paper-based exploration on dilation and then define and talk about the properties of the non-isometric transformation of dilation, and then spend the last part of the lecture on, well, how can we use technology to support, or I guess display, these things to our students. So what is transformational geometry? It's just the study of shape understood according to the size and shape preserving actions of reflection, rotation, and translation, as well as the shape preserving action of dilation. So these are the things that we teach our students: reflection, rotation, translation, and dilation in K-12 mathematics. And it's the idea that, in geometry, one of the things that, if we have shapes, shapes sometimes move, and we want to have a way to account for that in mathematics. So let's do a paper-based exploration, and it's on reflection. So what we're going to do first is fold a piece of paper in half to form two half planes, P and Q, and a fold line M. Then we're going to open the paper back up, and we're going to draw three different triangles. So for triangle 1 will have three vertices in one of the half planes in P. Triangle 2 will have two vertices in one half plane with one vertex in the other half plane. And the last triangle will have two vertices in the half plane P and then a vertex on the fold line M. So once we've drawn those triangles, we're going to fold the paper again, and then we're going to transfer the location of each vertex across the fold line using a push pin, or if you'd like, your compass point, which is what I'll use. And then we'll label the vertices of the pre-image and the image, so the first triangle and the new triangle, and then connect corresponding vertices with dotted lines and compare results, and see if we can find properties of reflection. So this is the way I usually teach reflection whenever I teach it for the first time. I think it's a good way to do it because you can discover the properties of reflection if you're careful about this. So let's go ahead and switch over to the Elmo Cam, and we'll go ahead and conduct this little. Okay, so I have a piece of paper. I have a very dirty surface here. I'll clean it off a little. So I'll take the piece of paper. I'm going to fold it the hot dog way, just so that we have a, I don't know, it seems to work best if you do it that direction. So there it is. The paper's folded in half, and we have now two half planes. I'll call them P and Q. So that's what I mean by half planes, P and Q, and then a fold line M. I guess you could draw it M, but I'll just assume you understand that if I put M on the fold line, that means this line. So half plane line. And then what we're supposed to do is draw three different triangles, one with all three vertices in P. I'll put a B, and C here. I don't know. And then one with 2 points in P, 1 point in Q. So why don't I do I don't know, maybe we'll give it different. How about P, Q, and R? So there they are. And then the last one, we're supposed to have 2 points in P and 1 point on M. Let's see, so I'll do, I don't know, something like this. So, since I haven't acute and obtuse, I'll do something that looks a little bit like a right triangle, PQR, STU, how's that sound? S, T, and U. I'll go ahead and draw those in. So there they are, and now what we're supposed to do is sort of to transfer the points to the other side of the paper. You can fold it either inward or outward. I usually fold it the other direction and transfer to the other side by just sort of pin pricking here like this. So I'll have a P, Q. I have to turn this over and do R. And then I guess the last thing would be S and T. And of course, this one's on the fold line, so you're sort of literally right there. And then it takes some doing, but you can usually see them pretty good if you pricked it good enough. I guess these are the 3 points that are transferred from A, B, and C. So if this one was transferred from A, I'd call it A prime. This one from B, I'd call it B prime. And this one from C, I'd call it C prime. And do some sort of a so there we go. There's the first reflection across the fold line M. Let's see, I'll put this one here. That must be R prime. And then this one must be P prime. And then this one must be Q prime. So I'll go ahead and draw that in. So the reflection of PQR, PQR prime. And then the last one, this one must be S, and this one must be T, and that one must be U. So I'll go ahead and so there we have it. Those the 3 triangles. I guess sort of give you a good sense of how reflection works in 3 different cases anyways. And the next thing you're asked to do in I guess the previous slide is to connect corresponding points up by lines. And so that means to connect C to C prime, sort of a dotted line here. A to A prime. This is going to be hard for me because I don't have a long enough ruler. Let me grab one if I have one. I think I do. Well, I don't have a ruler, but I have this. Oh, here's one. Sorry, should have had that out earlier. Bigger ruler. I guess B to B prime be like this. I'm going to kind of do it sort of light. Try not to muddy the picture up too much. Something like that. Looks like that line is just along there. So that's sort of what we're getting here, and might be interesting at this point just to draw in the reflection line just to see it a little bit better. Maybe I'll do that highlighter. Looks like that's showing up okay. And the big question is, well, what properties do you notice about these lines that connect up corresponding points? I guess this would be an S prime, a T prime, and then U and U prime are both at the same spot there. So I'll let you think about that for a second. And properties seem to be evident in all cases about the line that connects a point to its image under reflection. So hopefully what you thought of was that, well, first of all, it seems like, if I kind of use maybe I won't muddy it up any more than I have to, but if we use the reflection line as sort of a center, it seems to make sense that when I poke this thing through, that this distance from here to the line of reflection should be the same as this distance from here to the line of reflection. I mean, if you just sort of think about the way you constructed it, that distance needs to be the same as that distance, right? Because of the way it's just poked through, right? That distance needs to be the same as that distance because of the way it's poked through, and this distance the same as this distance. So the first thing that I think you can notice is pretty easily, if you put little points in here where these things meet, you could say, that this distance is the same as this distance the same as this distance the same as this distance. This distance I'll use curvy ones, same as that one. Those two the same, and these two the same. Then I guess the last piece here is that this distance is the same as that distance, so I don't know, maybe a little hatch mark like this, even though that's sometimes used for parallelity. I don't know, something like that. So those two distances are the same. And then of course, the distance from U to the fold line is the same as the distance from U prime to the fold line. Oops, I'm off the screen. Because both are 0. So the distances are the same. The other thing that seems to be evident is that, if we hold a piece of paper up to the corner, it seems like, that's a right angle, that's a right angle, that seems to be a right angle, that's a right angle, that seems to be a right angle, so does that, so does this, so does that. So it appears that not only does the fold line bisect the line connecting a point in its vertex, in its image, I should say, under a reflection, but it perpendicularly bisects it. So all of these guys are right angles as well. And then the last thing you should certainly notice is that the two triangles are congruent under reflection. So, if this distance is the same as this distance, and this one are the same, and they're perpendicularly constructed, then the new triangle, the image, seems like it would make sense that it would have to be congruent. So in other words, this distance is the same as that distance, and this distance is the same as that distance, and this distance is the same as that distance. And you can kind of see why that would be. If you pinprick, here, prick, right? Then those distances are all the same here, here, and here. So by side triangle congruence, I guess, you can see that by construction, these two triangles should be exactly the same. Of course, that's true here and here as well. So congruent triangles result from a reflection. So just an idea, I guess, about how you might be able to teach this if you were ever to be tasked with introducing reflection. I thought it'd be nice if we started out with something hands-on today. So hope you like that. Let's go ahead and move on. So transformation, technically, let's define it. It's a transformation of the planes, a one-to-one correspondence from the plane to itself that maps every point in the pre-image to a new point in the image. So any transformation of the plane that preserves distances, that is, maintains congruency, is called an isometry. Iso meaning same, metry meaning measure. So the isometric transformations commonly taught in K-12 mathematics are reflection, rotation, and translation. Sometimes we relabel these, especially for younger learners, as mirror, turn, and slide. There is one non-isometric transformation commonly taught in K-12, and that's dilation. That transformation is sometimes referred to as scaling or enlarging, or if it's getting smaller, reducing. So that's it, a one-to-one correspondence. And the way that you should think about this is it's taking every point in the pre-image to every new point in the image. The way that you can think about this with regard to, I guess, the thing that we just did, let's enlarge it again. You know, we were able to take 3 points to 3 points and connect up lines, but there's no reason that we couldn't take, you know, some point, let's say here along this side, and take it to the other side too, right? I mean, A, B, C, let's call it D. And of course, D prime would be right here. So you can see that, you know, we can pick points along sides that are going to be mapped to new points, or any point in the interior would be mapped to another point in the interior, or a point out here. But I guess the point is that if this is the whole plane, then there's a rule, which is, you know, we're conducting using pinpricks, that takes every point here to a point here, and vice versa, every point here to a point there. So the point R would be one that's actually going across from right to left, whereas all the other ones we did were from left to right, or depending on how you look at it, I guess. But it's a rule, right? A rule that takes every point to a new point in the plane. Well, it turns out then that symmetry is related to this. In mathematics, we say that an object displays symmetry if it's invariant under one or more isometric transformations. So in K-12 mathematics, we commonly teach students about reflective symmetry, rotational symmetry, and translational symmetry. I'm not going to say a lot about symmetry today, but I will tell you that investigating for symmetry is I guess the topic of our problem solving activity for the week. So I'll leave that mostly open to investigation in the problem solving activity. So let's talk about the transformations that are isometric in grades 512. Translation is a transformation of the plane that moves every point in the plane a specified distance in a specified direction along a straight line. So in other words, this is the slide, right? And what do we teach kids about the slide? Well, sometimes we teach them on a coordinate plane, and this is really common. So on the coordinate or Cartesian plane, translations of function from the plane to the plane such that the image of the point with coordinates x comma y is x plus a and y plus b, where a and b are real numbers. So in other words, the a is how much I move it horizontally, and the b is how much I move it vertically. So that slide might have, you know, a horizontal and a vertical component, but either a or b could also be zero. It might be a fully horizontal or fully vertical slide as well. But that's the idea. If you have sets of points and you slide them, you'll get new sets of points, and all of them have to slide in the exact same way. So you choose an A and a B and apply it to all points. So what about rotation? Rotation is a transformation of the plane determined by holding one point fixed and then rotating the plane about this point a certain number of degrees, either clockwise or counterclockwise. We call the fixed point the center, and the angle is called the angle of rotation, and we always think of counterclockwise as having a positive angle of rotation. So three different Cartesian maps for 90, 180, and 270 degree rotations. Turns out that if we rotate by 90, the image of the point whose coordinates are x comma y is then negative y and x. The way I kind of try to think about this is that, you know, if you're rotating the plane 90 degrees, then x becomes y and y becomes x, right? If you just literally rotate the Cartesian plane. So that's one way to sort of think about why the switch of x and y. And then why does y become negative? It's because the x value, I guess, you know, becomes a negative y value because you're rotating it counterclockwise 90 degrees. So the x, which was vertical, now becomes the y. The y, which was vertical, now becomes the x, but it's pointing in the negative y direction, or in the negative x direction. So we have a negative in front of that. So if you rotate by 180 degrees, the image of the point whose coordinates are x, y is then negative x and negative y. And the way I kind of think about this is, it sort of makes sense to me, is that if you have something in the first quadrant, let's say 2, 3, and you rotate it by 180 degrees, then it seems to make good sense that it ends up in the third quadrant. We know that coordinates in the third quadrant have negative have all, both negative and x and negative y coordinates. So that seems to make sense to me, and it seems to make sense too that they would have the same x and the same y coordinate just in the third quadrant, which would make them negative. And then if we were to do 270-degree rotation, then the rule is that x comma y becomes y comma negative x. It seems like this makes good sense comparing it to the 90-degree rotation. We swap the coordinates, but in this case, instead of y being negative, the x becomes negative because we've rotated through 390s, I guess is the way I think of it. Okay, another way to think of it is to apply a 90-degree rotation to a 180-degree rotation in sequence, which would swap the 180-degree coordinates, so y would become a positive y in the x value. Okay, so these are things that we teach kids usually by investigating directly sets of coordinates that have been rotated. So what about reflection? This was the one that we investigated in the pen and paper activity. So if we reflect in a line L, it's a transformation from the plane to itself that pairs each point P with a new point P prime in such a way that L is the perpendicular bisector of P prime. So that's exactly what we discovered. As long as P is not on L, and if P is on L, then P is equal to P prime. If we just switch back to our picture, we can see that the definition is really borne out by the activity. Takes a point P to P prime such that this fold line, right, is the perpendicular bisector of the segment P prime. So long as P is not on M, right, in this case, then the point becomes itself under the reflection. So what's kind of interesting about reflection is all points along the line of reflection are mapped to themselves. Anything that's of course left or right of the line of reflection is mapped across the line to something in the other half plane. So there is kind of that interesting, I guess, caveat in reflection that so long as P is not on L, and if it is, then there is this fix that P is equal to P prime. So what happens with reflections? So it turns out that if you reflect in the x-axis, then x comma y becomes x comma negative y, and hopefully that makes sense. If you're reflecting in the x-axis, everything that's above the x-axis has to go below it, right? So the positive y becomes a negative y, and everything that's below it has to go above it. So if y itself is negative, then we just switch its sign and becomes positive. So reflecting in the x-axis just negates the y value of a coordinate. And similarly, if we reflect in the y-axis, then x comma y becomes negative x comma y. How to think about that? Well, if anything's to the right of the y-axis, then it has to go to the left of the y-axis. So that would make a positive x a negative x. If anything's to the left of the x-axis, it's got to go to the right of the x-axis, and that becomes, it switches the sign on the x. So a negative negative will become positive. I hope that makes sense. It also takes into account, well, what if x is 0 here? And if x is 0, then switching the sign doesn't change anything. So in other words, it maps all those points that are on the line of reflection to themselves. Well, let's try another pen and paper based exploration on dilation. I've created a handout, and the instructions are on the handout, and it says draw a 3, 4, 5 right triangle, call it ABC, choose a center of dilation, let's call it D1, outside of ABC, and then dilate ABC by a scale factor of 2 to obtain A prime, B prime, C prime. And then we're supposed to repeat that with the following centers of dilation: D2 inside, D3 at a vertex, and D4 on a side of ABC. Okay, so let me walk through this with you, and then I'd ask you to stop the video and try the next few on your own. So here's the handout, and it's available on the website for download, printing. So So we're supposed to start by drawing a 3, 4, 5 right triangle. I just think it's easiest to keep the triangle the same, to take a look at dilations and centers. So I guess what I'll do is I'll put put it right in the middle of the page. There's a 3, here's a B, 1, 2, 3, 4, and here's a C. So there's a 3, 4, 5 triangle. And then I'm supposed to choose a center of dilation D1 outside of ABC, and then dilate ABC by a scale factor of 2. So that means I can choose D1 anywhere, but I have to be a little bit careful because when I dilate, it's going to make it larger, and I need to leave space for that to happen. Perhaps it would have been better to put this down here in the corner, but too late now. Let's go ahead and put, I don't know, let's put D1 right here. Now, I really haven't said what dilation is, but the idea is that you just double the distance, or use a scale factor to determine how much the distance gets changed. So one way to think about it is I want to double this distance from D to A to find where A prime is. Now, I could use Pythagoras and try to figure out sort of what that distance is and then double it up here so that I find my new A prime. But probably an easier way is just to use horizontal and vertical movement. If I go over 3 and up 1, 2, 3, 4, 5, 6, so over 3, up 6, to double that distance I should go over, instead of 3, I should go over 6, so 3, 4, 5, 6. Instead of up 6, I should go up 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there would be my A prime. And one way to make sure I've done this right, of course, is that they should be collinear, right? If I doubled the distance using horizontal and vertical, what I'm really using is just slope, right? And so if I repeat the slope, then these guys should be collinear. Let's do the same thing with B. I go over 3, up 3. So that means if I go over another 3 and up and 1, 2, 3, this should be where B is. So that's my B prime. Again, those guys seem to be collinear. And then to get to C, I go over 3, 4, 5, 6, 7, up 1, 2, 3. So over 7, 1, 2, 3, 4, 5, 6, 7, up 1, 2, 3. That should be my C prime. And again, these guys seem to be collinear. That makes good sense. So my new dilated triangle is right here. A prime, B prime, C prime, dilated triangle ABC by a factor of 2 with center D1. So that's the idea. On the next one, you're supposed to repeat with the following centers of dilation. So what I'm going to ask you to do is just to repeat this procedure, but to change where D is. So the next one I want you to do is D inside of triangle ABC. So do that here. And then D3 at a vertex. So in other words, one of these A, B, or C is also D3. And then the last one, D4 on a side, and let's make it not a vertex since we already did a vertex over here. So in other words, you could pick D along a side here, or along the hypotenuse and maybe there, or along a side here. Try to find a lattice point. It's going to be easiest if you find a lattice point, so perhaps don't choose the hypotenuse for D4. Okay, I'll go ahead and stop the video right now, and we'll come back. I'll have these 3 done and we can compare what we get.